Hello everyone, and welcome to the online lecture for college algebra. In this video, we're going to cover one of the trickier sections of the course, section P6 on rational expressions. So let's start off by defining what a rational expression actually is, and anytime you hear the word rational in mathematics, it should bring fractions to mind, just like the rational exponents that we talked about back in section P3. And a rational expression is a ratio or a fraction of two polynomials. So an example of a rational expression would be something like x plus 1 divided by x squared minus 9. We've got a degree 1 polynomial on the top divided by a degree 2 polynomial on the bottom. Now, because we're going to have variables in denominators of fractions, we're going to have to be a little bit careful, at least in the beginning of this section, because there's a rule in mathematics that we never divide by 0. That is something that is undefined. 2 divided by 0 doesn't exist. And so there are going to be some values that you just cannot plug into these rational expressions. And so we're going to start off by talking about that, and we're going to call it the domain, because that's what it is going to eventually transition into once we start talking about functions a little bit later on in the course. And so we're going to say that the domain of a rational expression is the set of all real numbers. It starts off being anything except those that cause you to divide by 0. So the domain is all real numbers, but the ones that cause you to divide by 0. And the ones that cause you to divide by 0, we sometimes call the restrictions on the domain. So let's start off by finding the domains of some rational expressions. So what we're going to do here is we're going to look for the spots that would cause us to divide by 0. Those are going to be our restrictions. And then we're going to say that the domain is all real numbers except for those restrictions. And so a good way to go about this is we can make an equation out of it. If we want to know our restrictions, we're going to say our denominator, which in the case of part A, is x plus 1 times x minus 3, can't be equal to 0. And we're going to solve this exactly like an equation. This not equal to sign, you treat exactly like you would treat an equal sign in an equation. And so we've got two things multiplied together, not equal to 0. So by what's called the zero product principle, we're going to set each of those not equal to 0 and solve for x. And you can probably just look at this denominator, at least with a little bit of practice, and tell what numbers would cause you to get a 0 down there. And that would be, if you subtract the 1 across to the other side, a negative 1, and then add 3 to both sides, a positive 3. We will officially dive into solving equations in a little bit more detail in section 1.1 a couple of videos from now. You can double check your restrictions pretty easily. If you plug these back into the denominator, you should see what happens. If you plug in a negative 1, you would get 0 times negative 4, which is 0. It makes the left factor 0. And similarly, if you plug in positive 3, you would get positive 4 times 3 minus 3, or 0, which would also give you 0 in the denominator. And so our domain is all real numbers except for negative 1 and 3. And let me show you the format that we're going to write that in this section. It's in something called set builder notation. And so it starts with set braces, which are these little curly brackets. And then we write the domain is x such that, and when we use this vertical line in set builder notation, that's read as such that, x such that x is not equal to negative 1 or positive 3. Now, what you'll notice is that the 2x minus 3 in the numerator here did not come into play at all. The numerator of the rational expression has no impact on the domain whatsoever. All we care about for the domain is where the denominator, the bottom of the fraction, is equal to 0. So it really doesn't matter what's going on up top. Similar for part B, we want to know where does the denominator equal 0. What are our restrictions? We don't want it to be equal to 0. And you could actually solve it with an equal sign as well, as long as you just remember that those are the things you end up removing from the domain. And so 2 ways to solve this equation. The first one would be to factor. X squared minus 9 is the difference of perfect squares, x squared and 3 squared. So that would factor into x plus 3 times x minus 3. And then just like the previous problem, set each of those not equal to 0 and solve, which would flip the signs once you move the 3's across to the other side of the not equal sign. Or you could use the square root property here. Add 9 to both sides to move it across, and then take the square root of both sides. But remember, when you take the square root of both sides, and we'll talk more about this again later on, you end up with a plus or minus sign to compensate, which gives you the same 2 solutions that you get with factoring. All right, so for part 2 then, the domain would be x such that x is not equal to positive or negative 3. And you could either write it as plus or minus 3, or you could write it out separately like the one we did up above. Now part C has a little bit of a trick to it. We're going to need to be careful. So if we want to know where the denominator is equal to 0, we can look for restrictions by setting it not equal to 0. But if you tried to solve this like an equation, we would subtract the x across, or rather, excuse me, the 8 across to the other side. Then we would divide both sides by 3. And you've got x squared is equal to a negative number. Now we'll talk about imaginary numbers in the next section, P7. But when we're looking for domains, imaginary numbers aren't important. We're looking for real values of x that we plug in that would cause us to divide by 0. Think about what x squared means. No matter what number you plug in for x, x squared is always either positive or at the very smallest 0. X squared can never be a negative number, at least if x is a real number. And so this is an equation that has no solution. All right, again, same logic applies to the original denominator. No matter what, x squared is at its smallest 0. So 3 times x squared at its smallest would be 0. But then if you just add a plus 8 on top of that, the smallest this denominator could ever be is a positive 8. This denominator will never be equal to 0. So in other words, you can plug whatever you want to in for x. There's no danger of dividing by 0 in this case. So be a little bit careful. Don't get the restrictions mixed up with the domain. If our domain is all real numbers except for the restrictions, in this case, we have no restrictions. So our domain is just all real numbers. Everything works. Now the format this particular book uses for all real numbers is it just writes it out in this section. The domain is just written out like this, all real numbers, but you might be used to writing that with the stylized symbol for the set of real numbers, the R, and that's perfectly fine as well if you want to write your answer like that on an exam. So we've introduced the concept of the domain. Truth be told, that's not going to be super important for the remainder of the section. That's mostly just a preview of things to come a little bit later on in the course, once we start working with functions. The rest of this section is going to be devoted to simplifying rational expressions and doing operations with rational expressions. So we're going to start off with reducing rational expressions, and remember, these things are just fractions. So all of this ultimately just ends up corresponding to fraction math in the end. So it's worth a quick review of how we reduce fractions. If you've got something of the form a times b over a times c, then the a's will divide each other away, and that just reduces to b over c. What you need to be careful about is that if you have addition or subtraction in the mix, it complicates things. It no longer reduces. So if you've got something like a plus b divided by ac, that does not reduce. It is such a common mistake that students will try to reduce a denominator with part of the numerator. It does not work that way. So be careful. So the process we're going to do to reduce rational expressions in this section is, well, we're going to start by factoring the numerator and denominator completely. Because these are polynomials we're working with, if we factor it, we take essentially what is addition, and if we can factor it, it turns it into a product of factors, multiplication. So we're potentially taking something that doesn't reduce in its base form and turning it into something that we can handle, something where we can cancel out like terms. So once we factor both the numerator and denominator completely, we look for any common factors, and then we reduce. So let's take a look at an example where we're going to reduce some rational expressions, and there are a lot of examples in this section. So just be ready for that, because like I said, this is one of the trickier sections, especially in the early portion of the course. A lot of students have trouble with it, so I'm just going to work a lot of examples so we get plenty of practice. Since step one in our process is going to be to completely factor both the numerator and the denominator, and these are rational expressions, so we're working with polynomials here. If you're a little bit rusty on your factoring, I would recommend you check out section P5 as review. So with that said, let's just go ahead and get started. So for part A, we want to factor both the numerator and denominator completely to look for any common terms, because this thing does not reduce at all in its current form. In the numerator, we have a common factor of 2 in 2x plus 4. So we can factor that out of both terms. And in the denominator, we have a traditional quadratic, x squared plus 5x plus 6. So in this case, we're looking for two numbers that multiply to give us 6 and add to give us positive 5. And so we're looking for a positive 3 and a positive 2 in this case. All right, and so now that the numerator and denominator are factored completely, you can see we actually do have a factor in common, and that is the factor of x plus 2. And so that reduces away, and what we're left with is 2 over x plus 3. Same idea for part B. We're going to completely factor both the numerator and denominator. The top I'm going to leave as b minus a for now because there's no obvious factoring we can do yet. We're going to need to adjust that, but we'll see why in just a second. For the denominator, we have a difference of perfect cubes. So we have a formula for that. And remember the pattern. It's a to the first power, b to the first power, a squared, ab, b squared. And then for the signs, the way we remember it is SOAP, which means same sign, opposite sign, and then always positive for the last. So since this starts off as a minus, the S in SOAP, same, means we start with a minus, then the opposite sign would be a plus, and then the last sign is always a plus, no matter what, always positive. And so a cubed minus b cubed factors into a minus b times a squared plus ab plus b squared. And we are close to having something in common. In the denominator, we have an a minus b. In the numerator, we have a b minus a. These are actually different by a factor of -1. And so if you want to rearrange the order of terms in a subtraction like this, in addition, no problem. You can just swap things around without any issue. But with subtraction, what you can do is you can factor out a negative sign, which would change the signs of both terms, right? Just imagine distributing that minus sign back through, and it would go back to being positive b and negative a. And so by factoring out that negative sign, it becomes a positive a minus b. So you can flip the order by pulling a minus sign out. And so that's what we need to do here. That's a minus a minus b. And that's a trick we're going to use a lot in order to get factors with subtraction to line up like that. A squared plus ab plus b squared. And then the a minus b's will cancel, but that negative sign is still there. Remember, canceling in fractions like this is division. So if ever the numerator or denominator goes away completely, that's the same as dividing two things that are equal to get 1. And so what we end up with here is a negative 1 over the part of the denominator that's left, a squared plus ab plus b squared. Now, when you have something that looks more like part C and D here, where you see a bunch of terms with the same variables in them, but with different exponents, instead of factoring completely, a lot of times it's better just to factor out the greatest common power between all of the variables. So in part C, we're going to use this as an example for the trickier part D. We just have one term in the numerator, one term in the denominator. No addition or subtraction getting in the way. So what I'm going to do is, since x squared is the biggest common power of x between the two that's in both, the top I'm just going to leave as x squared, but the bottom I'm going to break up into x squared times x cubed. Again, this is just going to be the same as the properties of exponents, but this is mainly set up for the problem down below. And then for the z's, the biggest power in common is just 1. So the top z cubed, I'm going to write as z squared times z to the first power, so that I can cancel that out with the z to the first power down below. And so now that I've broken up the bigger powers into pieces that match up with the smaller powers, the x squares can divide each other away, the z to the first powers can divide each other away, and what we're left with is z squared over x cubed. Right? And again, so the idea is to factor out the greatest power in common, not the greatest power period. So if we do something similar to part D, we've got three things going on in all three of these terms. We've got a constant, which these are all even numbers, so at the very least there's a 2 we can pull out of these, but maybe something bigger. Then we've got u's in all three, and we've got v's in all three. So we're going to factor out what is in common between the three terms and then reduce. So let's start off with the numbers. We're looking for the greatest common factor between 18, 24, and 42. And the biggest number that would divide into all three of those, and you could do it in pieces if you have trouble seeing it, would be 6 in this case. So I'm going to pull a 6 out of both terms in the numerator and the one term in the denominator. The biggest power of u that they have in common is 2. So I'm going to pull a u squared out of all three terms. And then the biggest power of v that they all have in common is also squared. So I'm going to pull a v squared out of all three terms. So let's see what we're left with once we factor that out. So for this first term, if we divide out a 6, because that's what factoring is, it's division, that just leaves us with 3 left over. You can always double check by imagine redistributing. 6 times 3 would be 18. I pulled out a u squared, so 2 of the u's are gone, which means there are only 4 left over now. And I pulled out a v squared, which reduces that to a v cubed. For the second term, if we divide out a 6, that leaves us with a 4. A u squared would leave us with a u to the first power, and then a v squared, that's all of the v's. They're gone. For the denominator, we're just pulling the 6u squared v squared out of a single term. So if we divide a 6 out of 42, that would leave us with a 7. We pulled out u squared, so both u's are gone. And then we pulled out a v squared, so that would leave us with v cubed. Now that we've pulled out the greatest common factor between all three terms, those will divide each other away. And so what we're left with in this case would be 3u to the fourth v cubed plus 4u over 7v cubed. And again, please, please, please do not try to cancel out those v cubes. That does not work. It has to be a v cubed in every term of the fraction. And you can really visualize that with the factoring that we just did. This will not simplify any further. If you still had anything in common between all three terms, you could reduce further. That means you would have missed something in the first step, but that's fine. You can break it up into multiple steps as well. A couple more for extra practice, and again, at the end of the day, the difficulty in this type of problem is actually just the difficulty in factoring. If you're comfortable with factoring, the process of factoring and reducing is pretty straightforward. But if you're not, then you probably want to make sure you get a little bit of extra practice with factoring. So in part A, in the top, we've got that difference of perfect cubes again, a cubed minus b cubed. So a, b, a squared, ab, b squared. And then SOAP, same, opposite, always positive. And in the denominator, we've got a difference of perfect squares. And that always factors into just a lot simpler than the one down below. A plus b times a minus b. Is basically the reverse of the conjugate idea that we were looking at in the previous sections. And so just knowing those formulas is the difficulty of this problem, as I mentioned, because now you see a common factor. We've got an a minus b, which will divide with an a minus b, nothing else in common. So the reduced form of this rational expression would be a squared plus ab plus b squared divided by a plus b. For part F, we've definitely got some tricky factoring going on here. So let's see what's going on. In the numerator, this is a standard quadratic, although we're working with y instead of x, but I mean, that's just a name. It works the same way. We've got 9y squared minus 6y plus 1. So I'm going to use the British method of factoring for that, which is a very procedural approach. Anytime you're trying to factor something of the form ax squared plus bx plus c, although again we're using y's in this case, you're looking for two numbers that multiply to give you a times c, the quadratic coefficient times the the constant term, and the two numbers need to add to give you b, the linear coefficient, the coefficient of x to the first power. And so in this case, we're looking for two numbers that multiply to give us a times c, or 9, and then add to give us b, which is negative 6. So if they need to add to give us a negative number and multiply to give us a positive number, that means they have to both be negative. And two things that multiply to give 9 and add to give 6 would just be 3 and 3. So negative 3 and negative 3 are the two things I need. And so the British method of factoring goes like this. Once you identify what those two terms are, you split the middle term, negative 6y, up into two pieces based off those numbers we just found. So the minus 6y, I'm going to write as a minus 3y minus another 3y. Then we still have the plus 1 at the end, and then we factor by grouping. So in the first two terms, I've got a 3y in common that I can pull out, which would leave me with 3y minus 1. And then I want to see if I can factor something out of the second two terms that would give me the same thing. I want a positive 3y and a negative 1, so I need to change the signs. So I'm going to factor out a negative 1. Now I'm going to do greatest common factor one more time, because both of these have a 3y minus 1 in common. So if I factor 3y minus 1 out of both terms, that would leave me with 3y minus 1 left over. So this is actually 3y minus 1 squared. All right, so that's the numerator. The denominator is actually a difference of perfect squares again, although it's a little bit trickier to spot this time around. So we've got 1 minus 9y squared, but 9 is 3 squared. And remember properties of exponents. A times b squared is equal to a squared times b squared. You can distribute exponents across multiplication, but you can also reverse that process. If you've got the same exponent, you can kind of factor it out. And so 3 squared times y squared would be the same as 3y all squared. And 1 is a perfect squared because 1 is 1 squared. And so if we factor that using the formula above, a plus b times a minus b, in other words, first term not squared, second term not squared in both, that would be 1 plus 3y times 1 minus 3y. All right, so let's see. Do we have anything in common yet? Close, but not quite. We've got a 3y minus 1, and we've got a 1 minus 3y in the bottom. So once again, the terms are just flipped. So I'm going to use that same trick that we used earlier, and I'm going to pull out a minus sign. Now I don't want to pull it out of this top one because I've got this squared going on, although I could go back to writing it as 3y minus 1 twice if I wanted to. But I'm just going to pull the negative sign out of the bottom one instead. When I do, I'm just going to put the negative sign out in front of the whole denominator. So minus 1 plus 3y times, and then it becomes 3y minus 1. That 3y minus 1 will now cancel with one of the two 3y minus 1s on top. A positive divided by a positive, or excuse me, a negative, if you want to think of it that way. Whenever you have a minus sign like this and there's no addition or subtraction, this is just one term divided by another term, you can just pull it out front of the fraction, right? So a divided by negative b is just negative a over b. So we can write this as a negative 3y minus 1 over 1 plus 3y. This is not the only form you can write the answer in. You could do a lot of different things with that minus sign. So for example, you could instead distribute it through the denominator. So you could also write 3y minus 1 over negative 1 minus 3y. Or you could actually distribute it into the numerator as well. It's like dividing by negative 1. So a positive 1 minus 3y over 1 plus 3y, because I didn't change the signs this time in the bottom, I changed the signs in the top, would also work as an answer. A lot of different formats, all of them simplest form. So now that we've talked about how to reduce rational expressions, let's start getting into the operations. So we're going to cover multiplication, division, addition, and subtraction. And we're actually going to start with multiplication and division because those are the easier operations when working with fractions. So again, these rational expressions are just fractions when everything is said and done. So we need to make sure we know how to multiply or divide fractions. To multiply two fractions together, you just multiply their numerators and multiply their denominators, and you're good to go. To divide two fractions, well, we just remember that dividing by a fraction is the same as multiplying by its reciprocal. So you just flip the fraction you're dividing by, and then you multiply. Product of the numerators, product of the denominators. So that's what we're going to be doing here. But a key thing to keep in mind is that you can actually do what we were doing in the previous example. You can reduce, factor and reduce before you multiply to make the problem easier. Because once you multiply everything out, it gets harder to factor at that point. Now, I did specifically say multiply here. You don't want to try to factor and reduce while it's still in division form. So if you have a problem involving division, take the reciprocal and turn it into multiplication first, and then you can factor and reduce before you multiply still. Otherwise, things get a little bit hazy as to what cancels with what when you're still in division form. So let's take a look at some examples involving multiplication and division of rational expressions. And we'll start off with a pretty simple one in part A. So we've got 14w over 51y times 3w over 7y. Now, the letters won't cancel each other. There are no w's down below to cancel with the ones above, and there are no y's above to divide with the ones below, but the numbers we can reduce. Because 14 is 7 times 2, we can divide the 7 through that. And then 51 is 17 times 3, so the 3 will divide into that evenly as well, so we can cancel that. Which means what we're left with after all of that cancellation is done, in the top we've got 2w, or when multiplied together, 2w squared. And in the denominator, we're left with 17y, or 17y squared. Similar for part B, although we've got factoring with variables involved this time around. So I'm going to start, I'm not going to multiply yet, I'm just going to factor everything. So in the term in the top left, 2a minus 2b, we've got a common factor of 2 that we can pull out. I'm going to hold off on the denominator for now because I think that 6 is going to end up reducing with some of the stuff over here. So that's going to be, in fact, why don't we go ahead and do that as well? Because 6 and 9 have a factor in common 3, I'm going to write the 6 as 3 times 2, and I'm going to write the 9 as 3 times 3. And then there will be an extra a there as well. And then in the bottom right, we've got a difference of perfect squareds, a squared minus b squared. So that's going to factor into a plus b times a minus b. And now we've got a lot of stuff that cancels out. So we've got a 3 that's going to divide out of the fractions. We've also got a 2 that divides out, so that 6 actually went away completely. And then in addition to that, we've got an a minus b that reduces with the top left as well. And so let's see what we're left with. In the numerator, all that's left over is 3 times a. Everything else got reduced away. And in the denominator, all that's left, when all is said and done, is this one factor of a plus b. Again, that a will not cancel. Don't do that. The addition gets in the way. All right, so try pausing the video here and see if you can find the simplified solutions to parts C and D. And again, be careful, watch out, because D is actually division this time around. So part C, same as before, we're just going to factor. These are just both basic x squared plus bx plus c factors in the denominator. So for the one in the bottom left, two things that multiply to give positive 4 and add to give positive 4 would be plus 2 and plus 2. Not surprising we see that, by the way, if we expect this to reduce at all. And for the one on the right, we're looking for two things that multiply to give us a negative 3 and add to give us a positive 2. So if they multiply to give a negative number, they have to have opposite signs, a minus and a plus. And then I'm looking for a plus 3 and a minus 1 if I ultimately want to end up with a plus 2. All right, so again, not surprising that we see an x minus 1 involved, because this is going to reduce. The x minus 1 in the bottom right will reduce with the one in the top left. One of the x plus 2's will also reduce. And so in the top, it looks like there's nothing left. But again, remember, this is division, So if everything gets divided away, that's left with a 1. In the bottom, we're left with x plus 2 and x plus 3. And so this works as a final answer, but you could also FOIL out that polynomial in the bottom now and write this as x squared plus 2x plus 3x would give us a plus 5x, and then 2 times 3 would give us a plus 6. So either one of these would work as a suitable final answer. Part D is pretty much the same, just the extra layer of division. So to start off the division problems, before you start factoring and reducing, you always flip the fraction. Dividing by a fraction is the same as multiplying by its reciprocal. And now it becomes just like the previous 3 examples we worked. So let's see. 4 minus x squared is actually a difference of perfect squares. So that's going to factor into 2 plus x times 2 minus x. And that 6 I'm going to write as 2 times 3 because I'm going to reduce that 2 away in just a second. And this is 2 divided by x minus 2. But again, that's a flipped version of what we've got up here with the 2 minus x. So instead of pulling the minus sign out of this one and making that a separate step, I'm just going to go ahead and pull the minus sign out of this one now. So that's a negative, positive 2 minus x. Factor out a negative 1. Now that 2 minus x will reduce with the one above. That minus sign does not go away, so don't lose track of that. In fact, maybe it's better to write it as negative 1 times to make sure you don't lose track of it. The 2's will also reduce, and so what we're left with here is 2 plus x in the numerator divided by 3 times negative 1, or negative 3. And again, we have that situation where we've got a negative sign floating around, so there's a lot of different ways you could leave your final answer. This works. You could pull the minus sign outside of the fraction. That would work. Or you could also put the minus sign into the top of the fraction. But in this case, it would flip the signs of two things. You would get a minus 2 minus x, so that's probably not worth it. All right, so one more before we move on to addition and subtraction. Part E is pretty similar to the one that we just worked. So once again, try pausing the video and see if you can find the solution to this one. All right, so first things first, because this is division, I'm going to begin by flipping it. 25 minus a squared over 6 times the reciprocal, 8 over 2a minus 10. And then I'm going to start factoring. So once again, 25 minus a squared is a difference of perfect squares. So that's going to factor into 5 plus a times 5 minus a. The 6 and the 8 have some stuff in common, so I'm going to break those down into smaller pieces. The 6 is a 2 times 3. And this will be times 8, which I'm going to write as 2 times 2 times 2. You could write it as 2 times 4, but I broke that 4 up further because I see that I'm probably going to have an extra 2 in the bottom that I can divide away. But no big deal if you don't do that in the first step. And then for the 2a minus 10, let's pay attention to what's happening here. If I factored out just a 2, I would be left with 2 times a minus 5. But once again, this is a flipped version of a factor that we see in the numerator, 5 minus a. So instead, I'm going to factor out a negative 2 to change the signs of the terms in the middle, or on the inside of the parentheses. So that would be a negative 2 times 5 minus a. All right, and now we can do a lot of cancellation. 5 minus a's cancel, 2's cancel, more 2's cancel, but be careful, the minus sign is still there. And so what we're left with in the numerator is we've got a 5 plus a, still in parentheses, times a 2, divided by 3 times the negative 1. You can distribute that 2 through the parentheses as well. So you could write that as 10 plus 2a over negative 3, or you could pull the minus sign out of the fraction and write it as a negative 10 plus 2a over positive 3. So now that we've talked about multiplication and division, let's move on to addition and subtraction. And again, these things are fractions. So recall the way addition and subtraction works with fractions. You need to have a common denominator in order to combine fractions together with addition and subtraction. So if you've got a over b plus c over b, then you just add the numerators together over their common denominator of b. So it's a plus c over b. Subtraction works the same way. A over b minus c over b is just a minus c over b. The problem is, most of the time we're not going to start off with a common denominator. We've got to create one. So in order to figure out what the common denominator is, we're going to look for something called the least common denominator, or the LCD for short. What we're going to do is we're going to factor each denominator completely so that we can see what all of its components are. And then the least common denominator will basically be each factor that appears in every denominator with the highest power of that factor that appears. And we'll see plenty of examples of that very shortly, don't worry. All right, so let's take a look at some examples of adding and subtracting rational expressions. We start off pretty easy. In part A, 3 over 2x plus 4 plus 5 over 2x plus 4, because these actually already have a common denominator, which means we can jump straight into adding the fractions. So the numerator would be 3 plus 5, or 8, over the common denominator of 2x plus 4. That said, you may notice that now all of these terms are even. There's a common factor after we've combined them together. And so we can reduce this further by either factoring out a 2 and reducing, or just dividing everything by 2 if you want to think of it that way. Either way, we are left with 4 over x plus 2. Part B is a little bit on the trickier side because these do not have a common denominator already. So we're going to have to create one. So I'm going to start by fully factoring the denominators so I can see what factors make them up. So x minus 1 doesn't factor, but x squared minus 1 is a difference of perfect squares. So that's going to factor into x plus 1 times x minus 1. Now this is a relatively simple case, so you can probably just take a look at these two denominators and see what's missing in the one on the left. And if you can do that, that's fine. I'm going to go ahead and write out the least common denominator to show you the process of finding the least common denominator for when problems get a little bit trickier a little bit later on down the line. So what I'm going to do is look for each factor that appears and then include its highest power of it. So we've got an x minus 1 in both denominators. You only have to include it once. So that's one factor down, and then we've also got an x plus 1, so that's included as well. And that's all the factors. So this is the smallest common denominator between the two. Turns out it's already what the one on the right is. So we don't have to adjust it at all. All we have to do is take a look at the one on the left and see what's missing. It's already got the x minus 1, it's just missing the x plus 1. So that's what we're going to have to multiply in to get the same denominator as the one on the right. Again, that might have been obvious without writing out the LCD in this case, but this is practice for later. So I'm going to take this fraction on the left then, x over x minus 1, and if I want to multiply an x plus 1 into the denominator to keep the fraction balanced, I have to multiply by x plus 1 in the numerator as well. just like when we were rationalizing square roots. And I'm just going to go ahead and write that a little bit nicer. So not really a lot of math happening here. It says x plus 1 times x in the numerator, x plus 1 times x minus 1 in the numerator. And in fact, I'm just going to start writing the denominator LCD to save a little bit of space here. I won't leave my final answer like that. And so now that they've got the same denominator, x plus 1 times x minus 1, I can add. And so it's just x plus 1 times x, the numerator on the left, plus 2x plus 3, the numerator on the right. All over their common denominator of x plus 1 times x minus 1. Now, we can certainly make this look a little bit nicer. If I distribute that x through, I'm going to do this off to the side to save a little bit of space. The numerator would be x squared plus x plus 2x plus 3. And then we can combine like terms. And so we can write this as x squared plus 3x plus 3 divided by x plus 1 times x minus 1. Now it's worth checking to see if this would reduce at all at this point, but that polynomial in the numerator doesn't even factor, because you would be looking for two things that multiply to give you 3, which are just 3 and 1, and those add to give you 4, not 3. So you can't factor that thing on the top. So this is as good as it gets. You could leave your answer like this, or if you really wanted to, you could also multiply out that denominator again, which would take it back to being x squared minus 1. So now let's try one with subtraction, but the idea is the same. There's just one thing you're going to have to be careful about with the subtraction, but we'll talk about that in a second. So to begin with, we've got to make sure we get a common denominator, because once again, these denominators are not the same. So we're going to start by factoring the denominators to see what factors we're working with. So for the x squared plus 6x plus 9 in the bottom left, two things that multiply to give positive 9 and add to give 6 would be 2 3's. And in the bottom right, x squared plus 5x plus 6, two things that multiply to give 6 and add to give 5 would be a positive 3 and a positive 2. Now note that, be a little bit careful here. You can't reduce across subtraction or addition like we were with the multiplication or division before. So don't try to get ahead of yourself and start trying to cancel things out right now. The only reason we're factoring is so that we can find the common denominator. Now if an individual fraction reduces, that you can do. But otherwise, don't try to reduce across fractions. That's not going to work. So let's take a look at what we're working with. This denominator here, x plus 3 times x plus 3, is x plus 3 squared. Or you could leave it factored out. That's also fine. So once we start looking for what we need to create a common denominator, we've got a factor of x plus 3 in both, but we include the highest power that appears. Because there are two x plus 3's in this denominator, just having one over here is not good enough. It's also going to need to have 2. So we need an x plus 3 squared as part of our common denominator. And then the other factor we've got is an x plus 2. So this is what our common denominator should look like when everything's said and done. So once again, you can now compare this to our two denominators to see what's missing, what you need to multiply in. For the one on the left, the x plus 3 squared, that's just missing the x plus 2, so we're going to need to multiply that in. And for the one on the right, the x plus 3 times x plus 2, that's just missing one of the x plus 3's. So we're going to need to multiply that in. And so that's exactly what we're going to do. For the one on the left, need to multiply both the top and the bottom by an x plus 2. And for the one on the right, we need to multiply both the top and the bottom by that missing x plus 3. Be a little bit careful here. Whenever the numerator of the fraction has multiple pieces like this, and you're multiplying to get a common denominator, put it in parentheses, because you're going to have to multiply the entire numerator by whatever you're multiplying in. So we're actually going to have to FOIL that. So let's see what we got. I'm going to go ahead and multiply out the numerators and then combine. For the one on the left, if we distribute through, we have x squared plus 2x over our common denominator. So again, to save a little bit of space, I'm just going to write LCD. Minus the numerator of the one on the right. Those are conjugates. You'd get x squared minus 3x plus 3x, which would cancel. Minus 3 times a positive 3 would be a minus 9. Over the same common denominator, because you have x plus 3 squared times x plus 2. Now the other thing you need to really be careful about here, common mistake, is that once you combine these together, if you are subtracting, you also need to subtract off the whole numerator of the second fraction. Please be careful, super common mistake. So this is going to be x squared plus 2x minus all of x squared minus 9, which would change the signs of both. So that's an x squared plus 2 minus x squared plus 9. And then in this case, we can simplify a little bit because the x squares will cancel with each other, a plus and a minus. And then we've got a 2 plus 9, so we can write this as 11. And because this is my final answer, I can't just write LCD anymore. I'm just going to write it out in its factored form. 11 over x plus 3 quantity squared times x plus 2. And quick correction here, I missed something. When I was copying from this line down to this line, I dropped the x in that 2x. So that would still be a 2x there, which means that that wouldn't combine with the 9, so the final numerator would just be 2x plus 9. All right, so one more addition and subtraction problem to go. And this one we're now going to have 3 rational expressions that we're combining together, but they're all a little bit simpler to kind of counteract that a little bit. So we got 1 over x plus 1 over x minus 1 minus 1 over x plus 1. So we've got to get a common denominator between all 3 fractions in this case. So normally we would start by factoring all of the denominators, but none of these factor. They're already as simple as they get. So we're going to go ahead and start collecting all of the unique factors. From the first fraction, we've got an x. From the second, we've got an x minus 1. And from the third, we've got an x plus 1. And that's it. Our least common denominator is basically all 3 of the denominators together, multiplied. So for our fraction on the far left, the 1 over x, we're going to need to multiply it by both of the other denominators, x minus 1 times x plus 1. Whatever you do to the bottom, also do to the numerator. For our second fraction, 1 over x minus 1, that's missing the other 2 denominators, x times x plus 1. And then for our final fraction, we're going to have to be careful because this is subtraction. 1 over x plus 1, that's missing the other 2 denominators, x times x minus 1. And so let's see what we've got. For the first one, we've just got x minus 1 times x plus 1. The ones here aren't really going to contribute because those are just being multiplied, so it doesn't change the value. I'm going to go ahead and FOIL that out, which would give us x squared minus x plus x. They would cancel because these are conjugates. Minus 1 over our common denominator. For the second fraction, just distribute the x through. That's an x squared plus x over our common denominator. And for the last one, also distribute through. That would be an x squared minus x over our common denominator. So let's put it together. We've got x squared minus 1 plus x squared plus x, be careful, minus all of the numerator x squared minus x. Put it in parentheses. And so that's just going to flip both of those signs. So that's going to be a minus x squared plus x. And let's combine like terms. So we've got x squared plus x squared minus x squared. The minus will essentially cancel out with one of the positive ones, but we've got one left over. Then for x to the first powers, we've got x plus x. So that's a plus 2x. And then we've got a minus 1 left over at the end. And this is all over our common denominator. X times x minus 1 times x plus 1. Again, it's probably worth checking if this reduces at all, but again, you end up with a polynomial in the numerator that just doesn't factor at all. You would be looking for two numbers that multiply to give a negative 1, and the only integers that do that are negative 1 and positive 1, and those would add to give you 0, not positive 2, so no good. And also you could multiply out the denominator, but it's a little bit unnecessary in this case. But certainly possible if you wanted to. One final type of problem to go in this section, and this is dealing with something called complex fractions. So a complex fraction is a fancy way of saying you have one large fraction that contains smaller fractions inside of it. So as an example, you could have something that looks like this. All right, you've got these smaller fractions, 3 of them in fact this time around, inside a bigger overall fraction. We don't like that. We don't like smaller fractions inside of bigger fractions. So to simplify something that looks like this, there are a couple of different approaches you can take. The first approach is you can find the least common denominator between every smaller fraction in the problem, every subfraction, I'm going to call them sometimes. Once you find that least common denominator, you can multiply both the top and bottom of the fraction by that common denominator, and that will end up giving you something where these denominators will reduce away completely. So the fractions will be gone after that. All right, so find the common denominator, multiply both the top and bottom by that common denominator. Your other approach is to separate out both the top and bottom of the fraction. So focus on one piece at a time. Start with the top, get a common denominator and combine it together into a single fraction. Focus on the bottom, get a common denominator, combine it into a single fraction. So that basically becomes 2 addition or subtraction problems from the last example that we worked. And then at that point it becomes a division problem. One fraction divided by another fraction, you can instead multiply by its reciprocal and reduce. All right, both problems, or rather both methods, get you to the same result. It's really just a personal preference thing, and neither method really has any major advantages or disadvantages over the other. So let's simplify some complex fractions, and we're actually going to start with the example that we had on the previous slide. This 4 minus 3 over 4x. divided by 1 over x squared minus 1 over 6. And I'm actually going to work this one with both methods, but only this one. After this problem, I'm just going to go with the least common denominator method. So I'm going to start with the LCD method. I want to find the LCD between 4x, x squared, and 6. So the idea of factoring denominators we've only done with polynomials so far, but that idea also works with numbers the same way. Let me show you what I mean. So I know that there's a common term in both 4 and 6. They're both divisible by 2. So I'm going to pull that out. So I'm going to write 4x as 2. In fact, I'm going to write it as 2 squared x. X squared is just x squared, and then 6 is 2 times 3. And so just like before, I'm going to go through each denominator and collect the biggest power of each unique factor I see. So we've got a factor of 2, but the biggest power of that is squared from the 4. We've got a factor of 3, which, by the way, 2 squared times 3 is 4 times 3, which is 12. 12 is the smallest number that is divisible by both 4 and 6. So if you've got easy to work with problems like this, easy to work with numbers, you don't have to go through this process of breaking the constants up. This is just showing you an example of how it works the same way. And then for the x's, we've just got x and x squared, so I'm going to include the biggest power we've got, which is x squared. So our least common denominator between these three would be 12x squared. All right, that's the smallest number that all three of these would divide evenly into. So now I'm going to multiply both the numerator and the denominator, because you've got to keep it balanced. That's like multiplying by 1. It doesn't change the value of the expression, by 12x squared. And let's see what happens. And so for now, I'm not going to do a lot of multiplying out yet. So in the top left, we're just going to have 4 times 12x squared. In the top right, when you multiply a number into a fraction, it goes into the numerator. So that's going to give me 3 times 12x squared over 4x. And the denominator, 1 times 12x squared, would just be 12x squared over x squared. And then 1 times 12x squared would give me 12x squared over 6. And now if you found your least common denominator appropriately, all of these smaller fractions will reduce. And they'll reduce in such a way that the entire denominator goes away. So in the top left, we've just got 48x squared from the 4 times 12. In the top right, the 4 will divide into the 12. The x will divide into the x squared, and we're just left with 3 times x, or 9x. And the denominator in the bottom left, the x squareds cancel perfectly. And then in the bottom right, the 6 will divide into the 12, leaving us with a minus 2x squared. And so this would be the simplified version of the complex fraction. All right, so again, I'm going to quickly work this the other way, just to show you the process. So same complex fraction that we have above, but now I'm going to treat the numerator and denominator separately. So in the top, I'm going to get a common denominator. Because this is basically a denominator of 1, I just need to multiply that 4 by 4x over 4x, which, again, that 4 goes into the top. So that would be 16x over 4x. minus 3 over 4x. And the denominator, neither of these have anything in common, so we're just going to multiply them by each other. So the one on the left I'm going to multiply by 6 over 6. The one on the right, x squared over x squared. And then I'm going to combine. So on the top, that's a 16x minus 3 over 4x. On the bottom, that's a 6 minus x squared over 6x squared. And now it's a division problem. So this is the top fraction, 16x minus 3 over 4x, divided by this, or multiplied by the reciprocal, 6x squared over 6 minus x squared. And then we reduce. So 1x will cancel. We can reduce a factor of 2 out of both the 4 and the 6. And so we're left with, in the numerator, 16x minus 3 still times this 3 and this x left over on the right. And in the denominator, we've just got 2 times 6 minus x squared. And if you distributed both that numerator and denominator, it would take you right back to the 48x squared minus 9x over 12 minus 2x squared that we got as the solution to the previous problem. All right, so again, just two different methods of working the same problem. They'll both get you where you want to go. There's not really any big advantage or disadvantage one method has over the other, so it's really just your personal preference, however you prefer to tackle this type of problem. All right, so we're going to do a few more. Starting with part B, we've got another complex fraction. And again, from here on out, I'm going to stick to just using the least common denominator method. I think it has a little bit more work up front because you have to find the common denominator between more fractions than when you're looking at the numerator and denominator individually. But you also end up with a little bit less reduction later on in the problem, so it kind of balances out that way. So first things first, if I want to find the common denominator between all of these subfractions, I need to factor their denominators so I can see what they're made from. And I can't do much here. All I'm really doing in this step is factoring the x squared minus 9, which is a difference of perfect squares. So it's x plus 3 times x minus 3. And so once we start putting together our common denominator, this one's actually a little bit nicer than the last one, I think. We've got a factor of x minus 3, but it only ever shows up to the first power. And then we've got a factor of x plus 3, which also only shows up to the first power. So our common denominator is actually the one that's already here up on the top. And so now I'm going to multiply both the top and the bottom of the fraction by our least common denominator, x minus 3 times x plus 3. I'm also going to take some shortcuts here with the simplification by thinking about what cancels as I go. So for the one in the top, once we multiply the x minus 3 times the x plus 3n, that's exactly what the denominator is. So it will just reduce with the x plus 3 and the x minus 3 on the bottom. It cancels out. So the only thing that's left over is the x plus 6 in the numerator. I said I was going to take shortcuts, but I guess I'll write this one out. Multiply it in, cancel it out. For the denominator, when we multiply this through to the first term, the x minus 3's would cancel. So the denominator's gone completely, and we would be left with x times the x plus 3. And when we multiply it into the term on the bottom right, the x plus 3's would cancel, and we would be left with, and be careful, there's a minus sign here. So I'm going to put all of this in parentheses. X plus 4, and because the x plus 3 is canceled, we're left with x minus 3. And an extra set of parentheses just to be safe. And that was pretty much the hard part. From here, it's just about multiplying out and combining like terms. So let's see. We've got x plus 6 over x squared plus 3x minus all of this polynomial, which if we FOIL would give us x squared plus 4x minus 3x, or a positive 1x, and then a 4 times a negative 3 would be a minus 12. I'm going to distribute the minus sign through now. So that would be a minus x squared. And I'm thinking of this as just the 1x. So minus x minus a negative 12 becomes plus 12. And then if we combine like terms, we've got an x squared minus x squared, a 3x minus x, and then a plus 12. Now, we're close to done, but we're not quite there, because if you take a look at the bottom of this fraction, you might notice that it looks suspiciously similar to the top. And this thing reduces further. If we pull a 2 out of that denominator, 2x plus 12 would be the same as 2 times x plus 6. So those also divide away, and this whole thing is actually just equal to 1/2, which is crazy to think about. This big messy thing that we started out with actually is just 1/2 when all is said and done. Next up, we've got a variation on the complex fractions problem type, and that's when you initially start off with negative exponents. So this doesn't start off looking like fractions inside of fractions, but it is because remember properties of negative exponents. If you've got something like x to the negative n, that's the same as 1 over x to the positive n. And so the trick is to write all of these as positive exponents first. So the x to the negative second would be 1 over x squared, the y to the negative third, 1 over y cubed, minus x to the negative third, or 1 over x cubed. And I want to pick something to multiply by that would cancel out all of these denominators. So we've got a factor of x. The biggest power that appears is x cubed. And then we've got a factor of y, whose biggest power is also cubed. So I'm going to multiply both the top and the bottom by x cubed, y cubed. So on the top, if we multiply it in, we'd have x cubed, y cubed over that denominator of x squared. Bottom left, x cubed, y cubed over y cubed, minus bottom right, x cubed, y cubed over x cubed. And again, all of these reduce. X squareds would cancel out 2 of the x's from the x cubed. Y cubes reduce completely. X cubes reduce completely. So what we're left over with is we've got 1x times y cubed in the numerator, x cubed in the bottom left, minus y cubed in the bottom right. Part D, a little bit more of the same. Another problem involving negative exponents, And it's going to go pretty much the same way, but be a little bit careful here. Once you start bringing negative exponents down to the denominator to make them positive, remember it only moves the thing it's an exponent of. So that ab to the negative second you see in the bottom left, when you simplify that, the b to the negative second will go down, but that negative 2 is not an exponent of the a. It stays up top. So please be careful. It's a really common mistake once we get to equations later on in the course, where if you've got something like 3x to the negative second power, a lot of times I'll see students write that as 1 over 3x squared. But it doesn't work that way, because the negative second is not an exponent of the 3. So that would just be 3 over x squared. Same idea here. All right, so with that said, I'm just going to rearrange this. A to the negative 1 is just 1 over a. B to the negative third would be 1 over b cubed. AB to the negative second would be a over b squared. And BA to the negative fourth would be b over a to the positive fourth. And so now if I look for a common denominator, clearly all we have are a's and b's here. Our biggest power of a that shows up is a to the fourth. So that's what I want to multiply through. Our biggest power of b that shows up is b cubed. So that's our least common denominator. That's what I'm going to multiply through the fraction. So in the top left, we're going to have our common denominator over a, because we're just multiplying by 1 in the numerator. Over b cubed in the top right. Now we've got some stuff already in the numerator in the bottom, so be careful. In the bottom left, it's going to be that a times, or a fourth b cubed. And in the bottom right, it's going to be b times our a fourth b cubed. And let's see how this reduces. So in the top left, the a will cancel out one of the a's on top. In the top right, the b's divide away completely. Bottom left, the b squared will cancel out 2 of the 3 b's on top. And in the bottom right, a to the fourths cancel each other out completely. So let's see what we're left with. In the top left, we still have a cubed, b cubed. In the top right, we've got an a to the fourth. In the bottom left, there's a lot going on here. We've got an a times a to the fourth, which is an a to the fifth, and we've got one b left over from that reduction. So a to the fifth times b. And in the bottom right, we've got b times b cubed, which would be b to the fourth. There is no common factor between all 4 of these terms. So there is nothing we could factor out and reduce here, because we've got one term that just has a's and one term that just has b's. Nothing cancels. And so this is as good as it gets. All right, and so that is it for section P6, one of the heavier sections in the earlier portion of the course. So don't get discouraged. Things lighten up a little bit next time around. As far as types of problems go in this section, there's a little bit of variety. First, be able to find the domain. It feels like it's been a while since we've done that, way back at the beginning of the video. That's just all real numbers except for the things that cause you to divide by 0. Make sure you can reduce rational expressions, which means that you need to be able to factor polynomials as well, because that's part of the process. And then we've got operations. Multiply and divide rational expressions, add and subtract rational expressions. That's the type that causes you to need a common denominator. And then we've got the simplifying complex fractions at the end of the section. As always, if you guys have any questions about the material, please make sure you let me know, and I will see you in the next video.